Welcome everybody, good time of the day. And let's start the session. So we'll probably go in the order that papers are listed in the schedule. And for every paper, we'll take a couple of minutes for the author to summarize the paper, the main results, and then we'll go to questions. Okay. So let's start with Martin. If you like to share your screen and say in a couple of words.
Okay, while we wait for my screen, hi everybody, I'm Martin, and I'll speak about bounded tree depth homomorphisms. Let me just show you the setup. I hope you can see it. So the setting is the following. We have a class of graphs here, okay? In our case, these are graphs of bounded tree depth, but at the moment it's just some class F of graphs. We have another graph G, and we look at homomorphisms from all these graphs in the class F into G. So all these arrows are supposed to be homomorphisms, edge-serving mappings between graphs. And we want to count these homomorphisms. So we get some numbers, 15, 267, whatever, and so on. Okay, and we collect all these numbers in a vector we call hom f of g. So what we can do this way is, if we fix the class f, we have a mapping that maps graphs into some infinite dimensional vector space. Okay, like this. So a vector embedding of graphs, and these have many applications, are quite interesting. And my result in this paper is the following. I look for F. I look at the class of all graphs of tree depth K. Maybe you know tree width better. Basically, tree depth is like tree width, except that we bound the depth of the tree as well. And then the result is the following. Two graphs are mapped to the same vector, two graphs G and H, if and only if they satisfy the same sentences of first order logic with counting, where we bound the quantifier rank to be K. So the quantifier rank corresponds exactly to tree depths. Now the context of this result is a list of related results where we look at these homomorphism embeddings. Actually, the notion of homomorphism indistinguishability, that means that two graphs are mapped to the same vectors, and characterize it by all kinds of natural relations, some of them algebraic, some of them logical, and we even have a correspondence between homomorphism indistinguishability over planar graphs and what is called quantum isomorphism. So this is quite fascinating. These homomorphism counts seem to reflect natural properties of graphs, and yeah, my result is one of the results that we have in this line of research. So if you have questions, please ask.
Yeah, questions, comments?
I guess I have a question. So you have this characterization in terms of logic. Do you think that there is any other kind of way of describing it? I guess what I'm thinking is that for, I think, tree depth 2, you just get the stars, right? Is that correct?
Tree depth 2 would be just the stars, yes.
Right, so this is just telling you the degree sequence of your graph.
Yeah.
Right. So could you have something where instead of having the sequence of degrees, maybe you have like, you know, the degree and then like the number of things at distance 2 or something like this, some more kind of information, kind of like but still just some kind of numbers or whatever. And this is equivalent.
I looked at this and thought about this. If I had something, I mean, I would like to have a characterization, so maybe in terms of some equations or so on. But this didn't work out, and the reason is somehow that since I cap off the depth, this is there is no iteration that closes at some point that distinguishes this result from some other result. So when I tried an algebraic characterization, I always had to fight with this thing that it stopped at a certain level. So I didn't find anything, but it's a very interesting question, and basically my answer is I don't know, but yeah, at least I've tried.
Yeah, the sort of the restricted depth thing is kind of a bit weird, I think, in comparison to the other sorts of results.
Yeah, well, in terms of logic, it's very, very natural. I mean, when we think of a logical formalism, looking at the quantifier depth is a very natural measure. It's also relates to other results in logic which talk about locality and local properties of structures. And there, roughly, it corresponds to the radius of neighborhoods we look at, because bounded tree depth graphs would map to bounded neighborhoods. So this bounded tree depth homomorphism somehow look at local properties, strictly local properties. So from that point of view, it's natural, it's true, and it doesn't fit very well into the more algebraic framework. And I don't know if it's not possible to, or if I just don't see it. So.
Nice.
Can I ask a question?
Please.
Hi, Martin.
Hi, Janos.
So in your theorem, you say sentences of first order logic with counting. Actually, you could make it infinitary logic as well, couldn't you?
I could, yes.
Because, I mean, once you have counting, it makes a difference. Even with bounded quantifier rank, you can get infinitary formulas which are not first order.
Look at equivalence. The thing is, here we look at
exactly. Well, but I was thinking, so this also gives us a normal form for these infinitary formulas, basically one big conjunction over the counts.
Yes.
And this normal form doesn't have equality. So you've got rid of equality.
I haven't thought about this. I mean,
because it's homomorphisms, so you don't need equality.
Yeah, that's true. I mean, one thing I noticed is that you somehow get rid of quantifier alternation and alternation of, say, Boolean connectives and quantifiers.
In fact, you can get rid of negation as well.
Get rid of equality. I haven't.
No, it's just a curiosity. I noticed.
Yeah, it's that's true.
Okay.
That's very nice. More
can
questions?
I have a question?
Yeah.
Hi, Martin. So this is Yujia. So can you say anything about the exact complexity of this homomorphism indistinguishability concern with respect to bounded tree depth?
Okay, so the question is, can I say how difficult it is to decide if two graphs satisfy this? And I think it can be done in polynomial time. I was wondering if it's maybe fixed parameter tractable in terms of the tree depth, but that I don't know. That's open, and maybe you would guess you can do it in fixed parameter tractable time, but I couldn't prove that either.
But can you do this in AC0, so even lower than polynomial time, if I'm not worried about A?
I don't know. I mean, you know, I wouldn't want to guess. It's probably more TC0, if anything, though, because you have this counting after all, and that must show up in the complexity, wouldn't you think so? But I don't know.
Yeah.
You're the expert on these things, so.
Yeah.
Good. More questions, comments? That's great.
Maybe I have one more. You mentioned in the talk the possibility of graphs of, say, bounded degree distinguishing all graphs. Do you think that's the case, or why or why not?
That's a very good question. I always thought it was the case, but the more I'm thinking about it, the more doubts I have. I think we can prove that at least for trees, so for example, binary trees are not strong enough, although we haven't written this up completely. I think we can prove that, and that was difficult enough. And I just don't know how to prove anything about the bounded degree. So I'm undecided there, and I'm really stuck. But I think it's a problem that can basically be solved. But I just have to think about it more, or maybe you do.
Maybe I've thought about it.
Okay.
But I mean, there are many interesting questions along these lines here. The things that we really don't understand. This is when we bound the degree, we lose this ability to do interpolation-like reasoning, as I'm using here. I make the degree large, and that gives me enough numbers so that I can do an interpolation and get this. And as soon as we go to bounded degree, we must do something else. To do something else in your plain stuff, even for the simple case of paths, we had to rely on a spectral argument. So as soon as you bound the degree, well, in a sense, it gets more interesting.
Okay, maybe time for one more last question, if anybody has a question. Okay, I'm very tempted to ask one. So before you had beautiful connection between counting logic and proof systems, polynomial calculus. Does this new result kind of comes in and says something about something more about polynomial calculus? Because it also relates.
Good question as well. When I was thinking about algebraic characterizations, I was thinking in particular about the relation of Nullstellensatz calculus and polynomial calculus. And it seemed to be related because this is more static than polynomial calculus. Polynomial calculus is somehow unbounded depth. It's more related to tree width than tree depth. So that was the stuff I was thinking about, but couldn't make it work. But still, maybe someone looking at it from a more proof complexity angle can see something I can't. That's certainly a very good question.
Thank you. Okay. Unless there are more pressing questions.
I had a question.
Yeah,
yes,
please. Yeah.
Yeah, I had a question about the main result, the main theorem. I was wondering whether there would be any chance of having sort of a refinement when you take into account the counting constants. So all your quantifiers are counting at least, let's say, P. Mm-hmm. And so is there any chance that there will be something, a corresponding measure of this these counting constants on the parts?
You're thinking of counting mod P or something like this?
Maybe not mod P, but something that would, on the algebraic part, represent.
That would be interesting, and I don't know, is the short answer, and maybe I shouldn't steal other people's time.
That's okay.
This is related to other questions about, maybe let's just stop it here. We can take it offline because I think we're kind of running over time here, right? That was my impression, at least.
That's okay. You could take a minute or two.
So we have these algebraic systems that are related to this, where I was always wondering about solutions over finite fields and if they correspond to something logical. And say if you take these systems of equations that typically characterize such equivalences, and then look at solutions just in a say in a GFP. Then I was always wondering what a logical characterization of that might be. And I never had a satisfactory answer. It's also related to stuff Anush has always been doing with rank logics and so on. But we don't really understand this very well. There might also be a more direct relation between the homomorphism counts and the algebraic thing without the logic, but I don't know. This is an interesting field there and interesting questions, but we don't have good answers yet. Certainly the logic with counting mods P is much weaker.
Mhm.
Yeah, thanks.
Let's probably move on to the next paper. Thank you so much, Martin. This was much more exciting than discussion than good. So how about Marcos? You'll give your 2-minute overview.
Yep. Sure. Does it work? Okay.
Yep.
Yes.
Okay, so I will quickly pitch our work on lower bounds for quantified Boolean formulas of bounded Treewidth, which is joint work with Johannes Fichte from TU Dresden and a colleague of mine, namely Andreas Pfandler from TU Wien. So what we presented is we established a complete picture of lower bounds for so-called quantified Boolean formulas, which are like propositional formulas, but we can have alternating universal and existential quantifiers. So what are the results? Well, we showed that under reasonable assumptions in computation complexity, namely the exponential time hypothesis, it is not expected to solve the validity of a quantified Boolean formula restricted to quantifier rank L in time better than L-fold exponential in the Treewidth. So the Treewidth is K here, while still staying polynomial in the instance size N. And the proof of our work is by reduction from any arbitrary QBF of quantifier rank L, and we construct a QBF of quantifier rank L plus 1. But what we gain there is we gain a significant reduction of Treewidth. So the Treewidth we obtain is exponentially smaller than the Treewidth of the QBF where we started from. So how do we do this? We do this by basically, so the reduction R is basically guided along a tree decomposition of our given QBF of quantifier rank L. And in this reduction basically tries to decouple structure, kind of decrease structural dependencies. And this is done via the additional quantifier block. But it's also quite important that we need kind of auxiliary variables or some kind of redundancy, but it's quite important that we not overdo it. So it's like a fragile balance between adding redundancy and keeping structural dependency low. And our result basically confirms the known upper bound for deciding validity of quantified Boolean formulas. So this is kind of ETH tight. And since our reduction is quite general, or say the technique we used, we think this is quite general. We also provided kind of a methodology to show lower bounds for QBF a bit simpler than it was, to show lower bounds for problems higher in the polynomial hierarchy for Treewidth a bit simpler than it was before. And we also included some showcases and new results for lower bounds for Treewidth. I think this is it for the short
pitch. If you have any questions, I'm happy to answer them.
Okay. We had a question on Slack from Uwe, but if you are here and you want to just
yeah, essentially, essentially the question has already been answered in Slack, but I can ask it once more. So, what about the constants that you had here in the estimation for the decrease of the size of the formula? I mean, you had a logarithmic decrease, but then you had some ugly constants, which mean in the worst case that you don't get a decrease if the original size is below 95 or so, the original tree width. And the question is, what do you get on the average?
Well, to be honest, this is like this is the reduction as is. It's like a worst case analysis. But the point is, in practice, you can probably do way better on special cases. I mean, I can also add this like to Slack. So I expect even better constants if one does this depending on certain classes of instances. So long story short, I would say this is really just a worst case like estimation.
Thanks a lot.
Yeah. But thanks for the question.
Yeah, more questions, comments?
Uwe, you had another question that was a bit more technical?
I had one question concerning one of the slides where I didn't quite get the notation. These squiggly arrows.
Yeah, sorry. I did not yet answer the question.
Yes.
So this is basically what we wanted to achieve with this outline is more to provide kind of an idea what we do here. But so the squiggly arrows kind of the information flow between variables, but using pointers. So if you look at the outline, and there are these blue squiggly arrows. This means that the information or the truth assignments of a copy variable is more or less copied to the green pointer variable, and then from the green pointer variable there is again a red squiggly arrow to a next pointer variable, which means that all the pointers are kind of synchronized via these red squiggly arrows. So this is really just like an outline or a sketch how, in principle, or how, just basically providing the idea what we're doing here.
Thanks.
Does this partly answer your question at least?
Yeah, partly.
I mean, I will also post.
One probably can't do much more here.
Yeah, I will post a link to. I mean, we got recent feedback, and it seems that in a solver of the CP community, this concept has been actually used, like using pointers to transfer values. It seems that this has actually. Maybe it's more clear if I just post the documentation of this solver. Okay. So there is like kind of a discussion how this is done, or how internally pointers are used in the solver. Mm-hmm. So maybe this helps a bit.
Yep.
Okay, more questions, comments? So just a very, very quick question. You mentioned that you have some non-uniform results. Like, how far can you push this technique?
Well, so far we did not try much, to be honest. We're just aiming, or kind of in the process of doing this. I would say it kind of depends whether we want to keep this technique a bit more general, or whether we want to have a look at special cases. But to be honest, at the moment, I cannot say much about this non-uniform cases.
Okay, looking forward to it.
Thanks.
Okay. If there are no more questions, shall we move to the next paper? Julian? So one thing about the paper the journal will be talking about, well, I guess I'm like half an hour ahead of everybody, but that's a special paper, and you'll hear in, well, a little bit over half an hour what was special about it. Then it got the Clinic Award. Julian, are you?
Okay, so let me share my screen.
Yeah.
Okay, so to sum up my presentation, we study in this paper the expressive power of successor-invariant first-order logic, which is defined from first-order logic with the addition of a successor relation, provided that we use this relation in an invariant way. So what is known about the expressive power of successor-invariant FO? Well, not much. Grunschwentig showed that they showed a more general result, but which entails that successor-invariant FO retains the Geifman locality of a plain first-order logic. Then Rossmann exhibited separating example showing that successor-invariant FO is able to express more queries than plain first-order logic, and his separating example involves dense classes of structures. So it is not clear whether on sparse classes of structures, having access to a successor in an invariant way adds to the expressive power of first-order logic. And quite the contrary, Benedict and Chegoufin showed that on trees, successor-invariant FO collapses to first-order logic, and that it is included in monadic second-order logic on classes of graphs of bounded degree and of bounded Treewidth. So the main theorem of this paper is that when the degree is bounded, successor-invariant FO collapses to FO. So the way to prove this is to start from two structures that have the same number of occurrences of each neighborhood type up to some threshold, and show that it is possible to construct two successor relations on them, S1 and S2, such that G1S1 and G2S2 still have the same number of occurrences of each neighborhood type up to some threshold. And without going into too much detail, let's just say that the main idea of the proof is to construct, for instance, S1 on G1, such that the neighborhood of most of the elements of G1 will be as regular as possible. And by that, I mean, will be a fractal version of the neighborhood of A in G1, which will look like something like that, and which helps proving that G1, S1, and G2, S2 have the same number of occurrences of each neighborhood type of the some threshold. So if you have any question, please ask.
Yeah, please, anybody? So, okay, question. That is very nice. Which other classes do you think, for which other classes do you think successor-invariant first order collapses to first order?
That's an interesting question and a hard question. I've looked at quite extensively at classes of bounded Treewidths, and it's really difficult in that setting, at least for me, to prove that successor-invariant FO collapses to FO. So it's it has been conjectured for quite some time, but I must admit that I'm not sure that it is true. And in any case, I have no idea how to prove that.
Very interesting. Yeah.
Can I comment on this? I mean, bounded Treewidths seems to be difficult because since the logic is local anyway, you wouldn't look very far, and then you're almost automatically already in bounded Treewidth. So I'm not sure what you can do. It seems difficult, I agree. But the other thing I wanted to ask, do you know anything about order invariant?
I'm looking at that at the moment, but in my opinion, well, I believe at least that order invariant also collapses to FO when the degree is bounded, but the proof of such a theorem would be, of course, more involved. And so
when we did the locality thing, we also, I mean, we basically set out to prove the successor invariant and eventually managed, and only then we noted that actually it can be extended. So.
And if I can ask a question, is the proof of the locality of a successor invariant much more simple than the proof of?
It's a long time ago, but I don't think so.
Okay.
That's exciting. Maybe I could figure something out. Conversation. So more questions, comments, ideas for how to prove things?
Can you say anything about succinctness? So if you have an equivalent formula in F0, what's the size? So
okay, so we have an easy lower bound, which is that successor invariant FO is at least as exponentially as succinct as first order logic. And this proof gives a translation which is a triple exponential. So I don't know if we can do better than triple exponential, but possibly yes.
Thank you.
Anybody else? Okay, I guess if you think of something you could ask on Slack, or you could talk about it on Slack or some other ways. Maybe let's then talk about the next paper. Josh, are you here?
I am.
Could you give you 2 minutes?
Sure, I shall just share my screen. Don't worry, I'm not presenting all those slides. Yeah, okay. Hello, people. So I'll just give you a very, very brief overview of what's in this paper. The paper is on QBF proof complexity. So it's giving us some results on proof complexity for quantified Boolean formulas. So first, just clarify what exactly is a quantified Boolean formula. It looks like this. You've got this propositional formula here, this phi, which is in these variables, the e's and the u's, and they're all quantified before this propositional formula. All the variables quantified in some linear order. So this thing's either true or false. All right, so this is your canonical piece-based complete language. So we're looking at trying to understand proof size in systems of logic for refuting these kind of formulas. And there are many, many systems, but the one that we're interested in is based on resolution, and we're interested in it because it corresponds to what's going on in solving. So we have this system and we want to prove some lower bounds, but we've kind of got a lead. We've got a lead because there's already a theorem here. In this system, so I'll just point you down here, this system here, which is based on the propositional Frege system. So this thing here, QNP Frege, it's just like you take the Frege system, you do something quite natural to it, and you get a QBF system out there. So then a propositional logic system into a QBF. And in fact, previous research managed to characterize hardness in this system as follows. So you have super polynomial lower bounds in this system if and only if P space is not contained in MC1. So that's non-uniformity. So what I really, really like about this theorem is that this is a proof system, right? And this is a direct connection between lower bounds in a proof system and lower bounds in a circuit class. So you make this direct connection between circuit complexity and proof complexity. With a long-standing belief in the community that these two things are linked. And well, in the QBF world, we have this very nice result here. It's a tight characterization of hardness in this system. So what we were interested in was trying to prove an analog of this result, where the base system here is resolution, right? So you can imagine this QNP resolution. This corresponds broadly to what's going on in solving. And we were interested in, can we kind of prove an analog of this result? So the answer is yes, we were able to prove an analog of this result. But only when we have bounded quantifier complexity, right? Or bounded quantifier rank, as you heard before. Provided the quantifier rank is bounded, then actually the size of the smallest proof in this system, right, the name looks a little bit different here, but it's just the same system with Gradle swap resolution. Size of the smallest proof here is polynomially related to the size of the smallest UDL. And UDL is a circuit class, right? So it's basically like decision lists, just with multiple outputs. So here we have, again, a direct link between proof complexity, right, sizes of proofs here, and circuit complexity, sizes of circuits. The unbounded case, we didn't manage to crack, but we do know that this model is actually not correct for the unbounded case, right? It's too weak. But nice that this works with bounded quantifier. So that's the first main result. And the second main result that came out of this is a size-width relation. Now, if you're not familiar with size-width, just try and sum this up very quickly. Basically, a lower bound technique that's come out of propositional logic, the resolution, polynomial calculus, which allows you to prove a size lower bound on the size of the proof by proving a width lower bound. Right? And in general, the width lower bound is much easier to prove. So you want to prove a size lower bound. Okay, I'll just prove a width lower bound, and then you apply this relation to it. Right? Turned out to be a very nice technique for proving lower bounds, and basically all of the known lower bounds, as far as I'm aware, could be reproved with this technique with shorter proofs. Okay, so what's interesting is that this relation has been ruled out for QBF. So previous research has shown this does not hold for QBF. But we managed to prove that it does hold with a few modifications. So you'll notice the initial width has gone from the numerator. We've got some d cubed down here. This is the quantifier complexity again, quantifier rank, and we've inherited some log n. But nonetheless, yeah, we were able to prove this theorem, and we were able to reprove a bunch of QBF lower bounds with very, very short and succinct proofs just by applying this relation.
Very nice.
That's everything I'd like to say. Yeah, thank you.
Very nice. Questions, comments? So, okay. If nobody, I'll ask a quick question. So for Benson-Wigderson, there recently been some more kind of game theoretic graph characterization of those proofs as a general framework for proving those lower bounds. Does this, Jakob was talking about it, Jakob Nordstrom, does the same kind of game characterization apply to your version of Benson-Wigderson, size width lower bound?
It's a good question. We're talking about prover delay games.
Yeah.
Yeah, and asymmetric prover delay games and so on. The short answer, I'm not entirely sure what the relation is. I can't concretely say that I can make any connection there. The longer answer, I think there might be some kind of connection. So kind of, as I think more about these things, I've been looking at more kind of game theoretic ideas. I've been looking at some more kind of characterizations of counter models and so on, which are more in line with perhaps not exactly proof of delay games, but evaluation games for QBF. And I think there may be a route to proving these lower bounds through that framework, if you like. I can't give you any more details on what that would look like at the moment, but yeah, it's an interesting kind of direction for future work, and yeah, I think there might be something at the bottom of that somewhere.
Nice. Thank you. More questions, comments? If you have a question, just speak up. Okay, maybe we'll have a minute or two at the end, and there is always Slack to ask more questions. So probably let's go to the next paper, Sasank. Thank you. Sasank, if you could share your screen and talk for a couple of minutes. Good.
Thank you. So I'll be talking about some simulation results for algebraic proof systems, and so which were somewhat surprising to us. So an important open problem in proof complexity is lower bounds for AC0P Frege, and algebraic proof systems were introduced to sort of try and transport some of the reasoning used in the corresponding circuit lower bound into proof complexity. So here's just a quick recap of polynomial calculus. So you're given a system of polynomial equations, and you're allowed to take linear combinations and multiply as long as your low degree. And the goal is to refute the system, that is to derive this contradiction. And so we have two parameters, so the degree and size, and they are related by this relation that was just talked about. We have strong degree and size lower bounds for pigeonhole principle and site and tautologies. Okay, so now here is the premise of our work, is that so we now have strong bounds for these algebraic systems, but they have led to very little progress for AC0P Frege, and so maybe the natural next step is to say maybe let's try to define stronger systems and try and prove lower bounds for them, and maybe we get more insights that way. So here we offer a reason why. Sorry.
Sorry, the airport.
Yeah, no, I guess like an Air Force base. Yeah. Sorry about that. So here we offer a reason why this approach of generalizing polynomial calculus might not work, because this generalized system turns out to be much more powerful than AC0P Frege, or it does things that we don't believe to be in AC0P Frege. So okay, so how do we generalize polynomial calculus? So we focus on this one particular generalization by Grigoriev and Hirsch, which is to introduce extension variables which are functions of original variables. So say we can define an extension which is a linear combination of the original variables, and then another extension on top of it, which is a product of these variables, and so on. So essentially we're building an arithmetic circuit over the original variables, and so we define the system depth dpc, which has d minus 2 alternating layers of sum and product, so that the final proof line is a depth d arithmetic circuit. And now the size is measured in terms of the number of monomials in all of these variables, which is sort of the natural way to measure size of a circuit. So what was known so far is already there were results hinting at the fact that this system is quite powerful. So when this system was introduced, Grigorian Hirsch showed that it can already simulate AC0P Frege if the depth is allowed to scale proportionally. And sort of the canonical hard tautologies for polynomial calculus are easy for even depth 3 PC. And finally, Raz and Samanet, they showed that so cutting planes with bounded coefficients can be simulated in depth 3 PC over rational numbers. And so sort of our main result, really, one of our results is that so we generalize this to unbounded cutting planes with unbounded coefficients and sum of squares. So essentially, we show that given enough depth, and this is a number that is just large enough. So depth DPC can simulate cutting planes with unbounded coefficients and sum of squares over an extension field, which is polynomial in the size of the proof that we want to simulate. Okay, so this is really our main result, generalizing from unbounded, the bounded coefficients to unbounded coefficients. And I'll just say a few things about it. So in this, so behind this result is really a result about Boolean threshold logic. Is that we know for circuits that a high weight threshold gate can be simulated by small depth majority circuits, and we have this tight simulation by Goldman, Hastad, and Rasparov. But usually the issue with these constructions is they use concepts like Chinese remindering, which are hard to kind of reason with in these bounded depth proof systems. So we had to use a much simpler but maybe less optimal construction, which just relies on bit arithmetic. And so our main result was to show that the correctness of this simulation can be sort of formalized in our system, depth TPC. And this really allowed us to extend the simulation to unbounded coefficient cutting planes. And so here are some open problems. So we first stated this open problem for proving lower bounds for polynomial calculus over this +-1 basis instead of the 0-1 basis, because this corresponds to these transformations where you go from a variable x to say 2x minus 1. So that is sort of the most the smallest non-trivial transformation you could make. And so this has since been answered by Sokolov. So other questions include just proving lower bounds for this system where you allow general linear transformations, and also we seem to need a large enough extension field in our simulations. So can we do the same over the base field, or show that it's not possible to? Okay, so I'll stop.
Thank you. So questions, comments? Thank you, Sasan. That's nice. Okay, just probably a very quick question. Do you think you will have results saying for this class of bases you can have lower bounds, and for kind of more in processing extending your bases over and over you can't? Or
Sorry, could you repeat that?
So if I understand it right, in your result, you add new variables multiple times?
Yeah.
What can you say about just pre-processing once?
Yeah. So in our result, we sort of fix the extension variables we want to introduce as part of the axioms, but I'm not quite sure.
That's okay. Just there seem to be lots of interest in direction where this can be taken, and I'm sure you thought about all sorts of things. Okay. We are a bit short on time, so unless there are other questions, last call. You always have Slack too. Okay, thank you, Sasan.
Yeah,
so let's go to the last paper, Matthew.
Hi, everyone. So I'll begin just by giving a short summary of the results in the paper, which, here's the first slide. So the thing that we study is called the hidden kernel problem. And that essentially takes as input two algebraic structures, A and B, and a homomorphism between them. The homomorphism is given as a black box. And as output, we would like the kernel of phi as generators or specified in some manner. Question, one good question is why bother studying this? Why look at this problem at all? And the answer is that this is a generalization of a problem that originates in quantum computation called the hidden subgroup problem, which is essentially the HKP, but restricted to groups. Many famous problems are actually special cases of the hidden subgroup problem. For instance, Simon's problem, which historically was the second computational problem to have a proven superpolynomial speedup on a quantum computer versus a classical computer. Shor's famous algorithm for factoring and the discrete logarithm problem on quantum computer are also special cases of the hidden subgroup problem when the group is taken to be either z or z squared. Another problem for which we don't have a quantum algorithm is the shortest vector problem. For this one, you essentially have, you look at a Q vector space and you look at a basis for that Q vector space. And then you look at the z-span of that basis, and you're asked to find the shortest non-zero vector in the z-span. So it's a difficult computational problem. That corresponds to the hidden subgroup problem on the dihedral group. And then the graph isomorphism problem, that corresponds to the HSP for the symmetric group. So it's a very important problem, and the hidden kernel problem is a generalization of that. In the paper, we consider the hidden kernel problem for Cartesian powers of a two-element algebra. So sort of a generalization of Simon's problem where you're looking at Z2 here. So we're looking at the HKP for an algebra that is b to the n with b to the n. So what are our results? Well, here they are. Essentially, we organize our search by examining the generating operations of the algebra, which means we're looking at post-lattice. And the theorem is that when the Boolean algebra that we're taking a product power of, when it falls inside one of these blue portions of post-lattice, then we actually have a polynomial time classical and quantum solution for the hidden kernel problem. When it falls into this sort of central purple area here, then we get super polynomial speed up, meaning we have a polynomial time quantum algorithm, but the classical algorithm is essentially brute force. You cannot do better than essentially a brute force algorithm. And then if you fall into the red portion of post-lattice, then for both classical and quantum computers, you essentially can do no better than brute force. And the sort of main landmarks in post-lattice are given over here, MPT 0 infinity, 1 infinity, and so on. Of note is AP0, which is essentially the group Z2. This was the only previously known sort of complexity that we had, and this is due to Simon. So this theorem is essentially two dichotomy theorems for classical and for quantum, and it can also be viewed as a very large extension of Simon's original results. And that's my quick 2-minute summary.
Thank you. So questions, comments?
Yes, I have a question. How do you get the lower bounds? I mean, what do you prove there, say for the purple or also for the red?
Yeah, so for the purple one, so you might think about like the very hardest version of this problem, which would be distinguishing the homomorphism either being trivial, namely just an isomorphism, or just sort of collapsing one up, so having a congruence which is an atom, right? And this is sort of the very hardest instance of this problem, because if you imagine classically, you know, if you're trying to figure out if something is an injection, you pretty much have to evaluate it a whole bunch of times and just see if you have any kind of collisions. So for the purple one, it's a sort of delicate counting argument, essentially showing that even if you allow for probabilistic computation, you cannot do better than essentially brute force. So it's a sort of delicate counting operation. For the red ones, we sort of select a very wide portion of the congruence lattice and show that first, there are exponentially many in the input size congruence is there, but that they also require exponentially large generating sets. So you can't possibly distinguish between all these different things and also output these very large generating sets in polynomial time. So that's the essential line of argumentation. Of course, you know, the question is there any other obstacle in the general hidden kernel problem? Is there any other obstacle to polynomial time solutions?
Thanks.
So there is another question.
Yeah, so I'm wondering if it looks reasonable to guess congruence distributive versus congruence modular versus dichotomy.
Yeah, that's entirely reasonable. That's entirely reasonable to guess. For the blue one, the blue are precisely the congruence distributive algebras. The result in the paper extends as long as you have the product of simple congruence distributive algebras. That's an entirely reasonable conjecture.
More questions? I thought there was at least one more question. Anybody? Okay, I guess the time is running out, so I'll resist the temptation to ask my questions, even though it's tempting. It's a beautiful characterization.
Thank you.
And you think of all sorts of extending it, all sorts of ways. But I don't want to hold people before the award session. So thank you very, very much to all the speakers and everybody who participated and everybody who asked questions. This is so much fun. And yeah, so if people have more questions, Slack channel will be open for some time, and please do talk. And I already saw some kind of new connections being established, even though it's online, which is way more than we could hope for. So thank you very, very much, everybody, and enjoy the award session.
The award session basically starts in 5 minutes, so please, please move
5
over.
minutes, okay.
Well, we just decided to move it a little. Yeah, but it's just move over. But yeah, enjoy the session. Thanks.